Hey everyone, so this is the second class of your organic preparation, and this is the next part, okay, of the name reactions. So first, the question: why don't simple aldehydes and ketones exist as enols? Okay, so the answer is given here that simpler carbon compounds like cyclohexane or acetone have a trace amount of enol formation in ordinary condition, and this is the formation here, and the energy diagram is also given here. Reason behind this is because the combination of a C double bond C and an OH single bond is slightly less stable, and the combination of a C double bond O and a CH single bond, okay. On the other hand, the OH bond in enol is a stronger bond than the CH bond in the keto form, but C double bond O of a ketone is much more stable than the C double bond C bond of enol, okay. So typical bond strength in keto and enol formation, these are this, okay. You just put in the uh, formation. Note, typical amount of enol is solutions are about 1 part in 10 to the power 5 for normal ketones, okay. So the amount of enol in equilibrium will carbonyl compounds also depends on structure factors. Next, aldehyde tend to have much higher concentration of enol than ketones. Why? So the reason is this. This is because of stability of carbonyl compounds. We know the ketone is more stable than an aldehyde because two alkyl groups donate electron density to the carbonyl carbon atom of a ketone, and versus only one for an aldehyde, okay. So in general, relative stability of double bond of a enol account for the amount of the enol formed, okay. The enol with more substituted double bond predominates. Here the k values are given. Note, however, the concentration of either enol is much smaller than the concentration of keto form, okay. So beta diketones provides a more dramatic demonstration of the effect of double bond stabilization on the amount of enol formed. Example, pentane 2,4 dione exists in the enol form to an extent of 76%. Fine. Okay. This is the formation, enol formation, and this is the keto formation. Okay. Reason behind this, the greater stability of enol form of a beta diketone can be attributed to an intramolecular hydrogen bonding between hydroxyl proton and nearby carbonyl group via a 6-member ring formation. This is the structure. Okay. So this is intermolecular hydrogen bonding is formed by 6-member transition state, and so this is the reason. Note, an intermolecular hydrogen bonding can stabilize a structure by 10 to the power by 20 kJ per mole, okay. Next, phenol is an extreme example in that the concentration of the ketone is practically negligible, okay. Reason, in case of phenol, keto form lacks aromaticity, okay, while the enol is aromatic and therefore significantly more stable. So this is more stable. Next, for more example, refer these books, okay. So next, equilibrium concentration for carbonyl enol tautomerization, okay. So this is the enol formation, okay. These are very less stable, but in case of beta diketone, this is more stable, okay, and the enol formation is greater, 76%. But in this case, this is largely exists in keto form, okay, cyclic diketone. Next, evidence that ketone and enol form exist in equilibrium. The fact that keto and enol form exist in equilibrium can be stabilized by running NMR spectrum in D2O solvent. Treatment of a ketone with traces of acid or base in D2O solvent leads to very slow disappearance of signal for protons next to carbonyl groups. All the alpha hydrogens are replaced or exchanged with deuterium atom, and this is the ketone enol form. But when the enol form reverts to the keto form, it picks up a deuterium instead of a proton, because the solution consists almost entirely of D2O and contains only a teeny amount of DOH. Okay, and this is the mechanism here. The process get repeated until all the alpha hydrogen gets replaced, and this is the mechanism. Okay, so you try with yourself. This is the mechanism, and all the reasons behind this are given here. If the compound is isolated from the solution afterwards, the mass spectrum also shows that the alpha hydrogens have been replaced by deuterium atoms, and peaks are absorbed at m+1 and m+2 instead of m+. Okay, so this is the mass spectrum. Okay, so you have to know the all the NMR spectrum and mass spectrum, the basics. Next, it is an example, that this is the example in D2O and DO solvent. Note, this experiment is also useful to determine the number of alpha hydrogen present in molecule. Okay. Since most of the reaction of carbon compounds are done in enol form or enolate ion form, so we first need to know how these enol and enolate ions can be generated. Okay, so formation of enol and enolate ions. Okay, and these are all aldehydes. This is aldehyde, ketone, ester, anhydride, and active methylene group. Okay, so in presence of active methylene group, the hydrogens are abstract by base, and a enol formation is generated. Okay, there are two methods by which above carbonyl compounds will form an enolate ion. Okay, first acid catalyzed and next base catalyzed enol formation. In acid catalyzed reaction, the molecule is first protonated on oxygen. First of all, protonated on oxygen, and then this hydrogen is abstract by which group and act as a base. Okay, so enol formed here. Okay, you just try yourself by this mechanism. Okay, and this is the formation, and the notes are here given. Okay, in case of base catalyzed enolization, in base catalyzed reaction, alpha hydrogen is removed first by the base. Okay, say hydroxide ion. Okay, and next proton is added to the oxygen atom in second step. Okay, this is the mechanism here. You just right. Next point to be noted, that in acidic condition we only get enol, but in basic condition we first get enolate ion and then enol. Okay, both of these reactions are genuinely catalytic, and both the acidic and basic catalyzed keto-enol interconversion occur rapidly in solution whenever these are traces of the acids and bases are present. Okay, and it is difficult to prevent keto-enol tautomerization even if case is taken to remove all acids and bases from the solution. Tautomerization can still be catalyzed by the trace amounts of acid and bases, and that are absorbed on the surface of the glassware. Okay, and fifth reason, the enol form is generally present only in small amounts, but it is very reactive, especially the alpha position is very nucleophilic, which can be justified with resonance structure. Okay, and this is the resonance structure. Okay, sixth reason, the reactions dominated by charges and electrostatic interaction occur on oxygen, whereas reactions dominated by orbital interaction occur on carbon. Okay, seventh reason, that is a reaction in basic conditions are generally performed by enolate ions. Okay, so these are the topics in this class. Okay, so basically we just put out the equilibrium constant and acid catalyzed and base catalyzed enol formation. Okay, so these are the topics in this class. Okay, next class I just give you that selection of base for enolate formation, and the next class is very important for you. Okay, so thank you so much.